Hello everyone. Promise this video will be shorter because I know 3.4.1 was way longer than I wanted to make it. When I finished, I said, dang, it's way too long a video. So I hope you wasn't too long for you and too boring, but this one will be quicker. So 3.4.2, how do you check differentiability algebraically? Right. And in addition to this, I'm going to show you something on your graphing calculator. So make sure you have your graphing calculator handy. So before anything, let me just quickly recall what differentiability means. So if a function f is differentiable, and remember that differentiable is really just the derivative exists, but the definition that you have to use is then 1, f is continuous, and 2, the derivative exists. Right? And I showed you last video that when we talk about the derivative existing, since the derivative is based on a limit, that just means that the limit from the left has to equal the limit from the right for every value in that domain. Okay. So really, a shortcut way of understanding is most functions that are continuous are differentiable. Now, also remember that if a function is not continuous, if not continuous, then not differentiable. Right. And last video, I went through all the examples that showed how that comes to be. All right. So if it's not continuous, it can't be differentiable. Right. So that's one way of knowing if it's not differentiable. Is if it's not continuous, then it's not differentiable. The other ways it's not differentiable, is if there's a cusp or a corner. And those are really the only situations when you're not differentiable. Is you're either not continuous or there's a cusp and a corner. Where you'll see on the worksheet that I created, because I didn't like the book problems there, a cusp is at both of these, f prime of x does not exist for some, there's a value of x within its domain that the derivative does not exist. And that's at that cusp and corner. Right? And at a cusp, the slopes more or less usually approach each other, but they might be undefined. And in a corner, they just approach from totally two different directions. Okay, but at both those points, the derivative does not exist there. So let's look at an example here. Let's look at, so prove the function, and I'll make a piecewise up to help you just, because really this video is I want you to see how to do this algebraically. And we'll say it's, x squared when x is less than 0. And then let's do x plus 1 when x is greater than or equal to 0. So prove f of x is not differentiable. All right, so let's show it's not differentiable. Now, graphically, you could say, okay, x squared, it would look like this. And then x plus 1, it would look like this. So informally, we could see that f of x is not differentiable since f is not continuous at x equals 0. It's not always clear, and that's why you want to check algebraically, because you're going to see in your in this worksheet that calculators, if you trust your calculator, sometimes off. Now, let me show you how to put this in a calculator, because one of your problems says how to put it on a domain. So if you go to y equals, and you put these functions in, so we have x squared. If you want to put that domain in again, you hit divided by, parentheses, and you're going to put in parentheses what you want. So x, and then you're going to go to the test button right above math. So hit second math, and we want to know when x is less than 0. And then close it. So that's x squared on the domain x is less than 0 is how we tell a TI-84 plus. And then we would say x plus 1 on the domain x is greater than or equal to 0. And then if you were to graph this, you'll see that the graph only graphs those domains. Okay? So that's how you do it on a calculator. Now, Now let's prove not differentiable. So we're going to call this value c, and we're going to use the definition, the limit as x approaches c of f of x minus f of c over x minus c. So we're going to pick some arbitrary value x and approach c from the left and from the right. So prove it's not differentiable. Well, if it were differentiable, then we'd say the limit as x approaches c from the left. So assume it were differentiable. This is called a proof by contradiction. Assume it is differentiable. Then, if it were differentiable, the limit as you approach from the left of f of x minus f of c over x minus c will equal the limit as you approach from the right. Right. So let's plug in our values and see what happens here. And note that in our problem here, we're looking at c equals 0. So maybe we just use that here. So 0 from the left. We're not trying to prove it for all cases. We just want to prove it at 0. Now let's see what happens. So if we're approaching from the left here, what function does f of x take on? Well, it takes on x squared. So then we're x squared minus f of 0, which we're approaching from left, so we're in this function. And 0 squared is 0, so that's minus 0 over x. And that's equal to the limit as x approaches 0 from the right of f of x. And now we're approaching from right, so we're on the function x plus 1. So that's x plus 1 minus f of 0, which you plug that in, you'd be at 1 over x. And if we simplify this, notice that on the left here, this is going to give you x. And over here, we'd be at x over x, which is just going to be 1. So what we get here is after we evaluate this limit, from the left, we have x. But notice that the slope of x, is not equal to 1. And therefore, we showed algebraically that the f is not differentiable. Since, if I wanted to get in words, since the limit as you approach from the left of the derivative is not equal to the limit as you approach from the right, which implies that f prime of x does not exist. F prime of 0 does not exist. And if the derivative of 0 does not exist, that means that the whole function is not differentiable. So there's a lot of little logic statements at the end there. But that's how you do it algebraically. I use this definition here. I think it's a little bit easier than using the definition with h. If you want to see how the definition of h works, I'm more than happy to show you. So I'm just going to note you could use the limit as x approaches h from the left of f of x minus h minus f of x over h, and the limit x approaches as h approaches 0 from the left, and then you can do as h approaches 0 from the right of f of x plus h minus f of x. So you can use this definition too, just slightly different. I usually use this one because it's what the book is going to use, and I'd rather stay on pace with what the book is going to be showing you. But if you want to try it that way, I'm more than happy to support you in it. Okay, so I hope that helps. That's how you prove algebraically, looking at the limits of the derivative from the left and from the right. And then hopefully you remember on a calculator that to get to the domains, you use the second test feature here. So you do a division sign, slash, and in parentheses, go to the test and use those inequalities to get the domain. All right? So that's it. Much shorter than the last video. Good luck.